Hey there, strangers. It's time for a 2 p.m. PST Twist stream. I'm your host, Strange for Jim. Today we're going to be getting ourselves into some coding today. Now, we have a bit to kind of work on today. We're in the next portion of our code where we need to start figuring out um, the pathing of our AI agents. And um, right now, um, I don't know whether or not A star is going to be, uh, I've used A star before. Don't know if it's something that I want to um, continue or not. So, I don't know whether or not that's something that is going to be very useful, or if there's something a little bit better for me. So, if there's a pathing algorithm that's better, then we're obviously going to need to go with that. But let's see, making sure everything is set up here real quick. Let's see. Okay, everything seems to be in relative order right at the moment. Let me make sure we got Chrome up and running so that we can continue our research on it. Or not on Chrome itself, but on A-star pathing. Okay, everything looks to be in relatively good order. Let's see. All right. Yeah, let's go ahead and get this live. Okay. So, um, we've been able to get our game working the way we kind of want it to, for the most part, in terms of the agents moving. Now it's a matter of time to uh, allow for them to kind of move around the map, or at least pick different destinations and have them move from where they currently spawn at to other locations. So we need to see whether or not we can get that up and running. Um, so while I go ahead and get the game up and running, we're going to continue our research in the pathing algorithms. So let's see, pathing or path algorithm from game. Let's see. Kama Sutra is a good site for anyone that is interested in, um, developing games. They have a lot of articles, and if anyone wants to kind of get into game development, Gamma Sutra is a good resource to know of or do. So let's see. Um, Path demo is available for readers to download. Square tiles. You can adapt the concepts of algorithms to other tiling, such as hexagons. Yeah. So let's see. Um, hmm, let's see. Situations where a star may not perform very well for a variety of reasons, more or less real-time requirements for games, plus limitations of the available memory processor time, and some of them may make it hard for even for a star to work well. A large map may require thousands of entities in an open and closed list. There may not be room enough for that. Even if there is enough memory for them, the algorithms used for manipulating them may be inefficient. Quality of a star search depends on the quality of the heuristic. If H is very close to true cost of the main path, its efficiency will be high. On the other hand, if it's too low, its efficiency gets very bad. In fact, breadth first search is an A star search. Hmm. Let's see. Hmm. Okay. I mean, we can hold on to this for now, but um, it's really not going too in depth into other algorithms. So let's see. What is the best pathfinding algorithm? Seems like a lot of people are still saying that A star is still the best out of it all. Which, I mean, don't get me wrong, it's still a really good pathing, but I'm not always in the, I'm not in the gaming biz, or at least I don't have a job in the gaming industry doing AI development, so I can't stay on top of all the research papers that are out there um, for new upcoming algorithms. So, so what we're gonna do is see. Um, hmm, let's go back to that one page, and the one Wikipedia page that actually had um, a listing of all the different kind of search algorithms, or at least try to find it. Nope, I'm going down the wrong rabbit hole. There we go. Okay, so I'm going to copy this list here real quick. And let's go ahead and try to do a good and bad of it all. Let's see. Let's see. Climbing. A lot of these I haven't even heard of before, so that's why I'm kind of interested in what these are offering. Now, some of them might not be that useful at all, but you know, um, if you're in the business of computer science or game design or anything along those lines, you want to try to find you want to try to find resources and code that will make things more efficient for you, you know, or you build it yourself. um, there we go. Okay, so um, good, bad. Okay, so I already know A star is going to be good for me, so that's a given. Um, I know Dijkstra is close to what A star is all about, but A star kind of beats out Dijkstra. So now we want to see which one of these is, you know, decent or might be a better search algorithm overall. So, um, let's see. Um, Here, let's go ahead and open this into a new window because we're going to be opening up a lot of tabs on this. So, and we'll just go one by one through the list and see if there's anything here that might be a, might be a little bit better. Obviously, I'm leaning more towards the A star, but I mean, we need to kind of do our due diligence on here. Okay, that is a lot of tabs. All right, let's just kind of pick one at random here. That first search. Um, Now, here's here's the problem with a depth first search. Um, our our tiles aren't really ordered in any one particular way. So, um, so the our node could be viewed as something that could be way over here. But the problem is that um, with the way our tiles are organized and like, yeah, let me bring up the game for those of you that might not be aware of it. We'll wait until that's done. Okay. Um, but with the map being the way it is, the the pathing could literally go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. You could literally have connectors going all the way to 12 from a single start point. So, and it might not be that efficient. So, um, so for example, um, if we're trying to reach this particular tile right here, well, this guy could travel, could just, kind of go back and forth, you know, across it all to just try to, get to that point up there. It could basically travel and traverse the entire map. Not exactly ideal. Um, and because um, What the heck is going on with my music here? It's not playing the playlist. Sorry. And no, I can't play it on my sound here, folks. Obviously, copyright is a pain. So, all right. So, as you can see, potential for um, you know, just there isn't like an ending for these nodes per se on this. Um, so the fact that it's a depth first search, meaning that it will go, you know, to all the way to the left in this particular case, you know, find no single nodes, come back here to this node and go searching through that. And if that's another long branch, then it will continue going down that road until it reaches its destination. And seeing that I have potentially multiple different paths going to a single destination, I mean, if it finds the path, it's not going to care whether or not it found the best path. So, so that's why this one's a little more concerning overall. So, not exactly ideal. So, um, so I'm going to go ahead and put depth first search in the bad section. Oh wait, I don't need to save it. What am I doing? Okay, so we don't need that. Dijkstra's algorithm, we've already kind of determined that it's good, but you can get a little bit of a better quality out of A star. So so you know, Dijkstra's is good, better than A star, not really. But I mean, if you want to research Dijkstra's a little bit more, you're more than welcome to. But um, I've I've already done prior research through classes and the like on this. So, um, okay. Edmonds algorithm. True Edmonds algorithm for finding a spanning instance of minimum weight, sometimes called optimal branching, is directed analog of the minimum spanning tree problem. Algorithm was proposed independently, first by Jin Chu and Hong Lu, and then by Jack Edmonds. Hmm. Hmm. Okay. In 1986, Gabo, Glynn, Spencer, and Compton, Tarjan produced a faster implementation with running time E plus V log V. Hmm. Now, I'm not mistaken. A-Star has a better version than that. Or at least um, its algorithm is better, I think. Hmm. Worst case performance. Yeah, let's go ahead and see. Worst case performance. Okay. Let's see, hold on. Dextras. Let's see. Let's see, worst case performance. Is big O E plus E log E. Now, this is interesting because um, Edmonds is saying the fastest implementation is, well, close to it. It's this one has the um, what's the word I'm looking for? Absolute value. So but it doesn't really give me a worst. Yep. Hmm. Okay. Gonna put this down in the bad because it looks like the best case performance is pretty much equal to the worst case performance for Dijkstra. So I'll get rid of the absolute values, but there we go. So you might be wondering, well, Jim, what's going on here? Why are you putting it in the bad? Well, so let's kind of put it along these lines. Okay. The best admins can do, like, this is the best value that admins can do is the worst for Dijkstras. Meaning Dijkstras can actually be faster than admins at its worst. So so that's the reason why I'm putting it in the bad. Now let's see. Um, Now depth first search, we didn't really record down its worst case performance here. There it is. Okay. There you go. Value V plus absolute value V. Okay. Um, okay, this is for explicit. And then we have O BD for implicit. There we go. Okay, now British Museum algorithm is a general approach to finding a solution by checking all possibilities one by one, beginning with the smallest. Term refers to conceptual, not a practical technique where the number of possibilities is enormous. This procedure, the British Museum algorithm, it seems to them to assemble placing monkeys in front of typewriters in order to reproduce all the books in the British Museum. Uh, okay, so there's really nothing to this in particular. Not exactly ideal. on that. Okay, let's see. So we can easily go ahead and put that down in the bad. Uh, no actual algorithm other than finding all possibilities. It, the sheer amount of calculations for that would probably get pretty insane. Um, so not exactly ideal. um, no worst case performance shown, but it really doesn't need one because there really isn't any kind of algorithm to it. So, okay. Hmm. Through related incremental search algorithms, original D-star, Stern's an informed incremental search algorithm. Focus D-star is an informed incremental heuristic search algorithm. Combines ideas of A-star and the original D-star. Focus D-star result development of the original D-star. D-star light is an incremental heuristic search algorithm by Steve. It builds on LPA and incremental heuristic. Combines ideas of A-star dynamic, including playing with the free space assumption. A robot has to navigate to a given goal coordinates in unknown territory. Makes assumptions about the unknown part of its terrain, for example, that contains no obstacles, and finds the shortest path from its current goal coordinates under these assumptions. Robot then follows the path and observes new map information such as previously unknown obstacles, and adds the information to its map, and if necessary, replans the shortest path from its current coordinates to given goal coordinates. It repeats the process until it reaches the goal coordinates and determines that the goal coordinates cannot be reached. When traversing unknown territory or unknown terrain, the obstacles may be discovered frequently, so this replanning needs to be fast. Heuristic search algorithms speed up searches for sequences of similar search problems by using experience with the previous problems to speed up the search for the current one. Assuming the goal coordinates do not change, all three search algorithms are more efficient than repeated A-star searches. Interesting. D-star and its variants have been widely used for mobile robot and autonomous vehicle navigation. When systems are typically based on D-star Lite rather than original D-star. Dynamic A-star because the algorithm behaves like A-star except that the arc cost can change as the algorithm runs. Maintains a list of nodes to be evaluated, known as the open list. Nodes are marked as having one of several states: new, open, closed. raise and lower. Raise and nodes changes to all other nodes. Hmm. Deadlock occurs. Hmm. Okay. Hmm. Let's cause current points. It's first entering open list. Hmm. It's not really giving me any kind of worst case or big O notation for it. So I might need to do a little bit more research on that. Let's go ahead and put this down potentially in the good, seeing that it's supposed to be um, it might be, you know, more efficient. We'll see. We'll see on that. So we'll need to research. Um, is showing worst case or research needed. More efficient and repeated A-star searches. So I'm going to need to look into that a little bit more. Matter of fact, let's go ahead and kind of save it for now. We'll move it back over to this window here. Same with the A-star. Right. There. Oh, wrong one. And okay. Iterative deepening A-star. Worst case space complexity. Hmm. Um, I'm not liking this. Unlike A-star, ID A-star does not utilize dynamic programming and therefore often ends up exploring the same nodes many times. Don't really like that. Um, its memory usage is lower than A-star. Concentrates on exploring the most promising nodes and thus does not go into the same depth everywhere in the search tree. Hmm. IDA star is beneficial when the problem is memory constrained. We don't shouldn't need to worry about that. So A-star search keeps a large queue of unexplored nodes that can quickly fill up memory, which is true. Um, but IDA star does not remember any node except the ones in its current path. So not exactly ideal. It doesn't. So a lot of these, is worst case performance, not worst case space complexity, but I'm not really all that interested in this one. So I'll go ahead and put down the worst case space complexity anyway. Um, okay, I'll make a note of this saying um, often ends up exploring the same nodes many times, which basically throws efficiency out the window on it. So not exactly ideal. Area deepening search or area deepening depth first search. State space graph search strategy in which the depth limited version will run repeatedly until increasing depth limits until the goal is found. Optimal light breadth first search and uses much less memory. In each iteration, it visits nodes in the search tree, same order as depth first search. The order in which nodes are first visited is effectively worst case is once again OBT. Oh wait, um, I went I went with the wrong one here. And this is what it was. There we go. Hmm. Has the same or similar worst case performance, but hmm, okay. Since area deepening visit states multiple times. It may seem wasteful, but it turns out to be not so costly since in the tree most of the nodes are in the bottom levels, so it does not matter much if the upper levels are visited multiple times. Hmm. And I'm not so sure about seeing that. Um, we're looking at the potential for um, seeing that we have the potential for it kind of exploring all the 6 nodes around it. So, um, you know, I could see someone just kind of running around in a circle, for example, um, thinking of trying to find a better path. So, hmm, hmm, I don't know. Don't really like the idea of it potentially searching researching nodes near the top of the tree over and over and over again. It might seem a little inefficient overall. Hey Jedi, how you doing there, bud? Long time no see. It's going pretty well for myself. How about yourself? Yeah, I think for the most part I'm gonna go ahead and put iterative deepening in our little bad section here. I'm not really liking that idea of, being able to research the root portion of the tree over and over again. So, let's see, Johnson's algorithm. First pass between all pairs of edges. Ooh, that doesn't look like a good. That doesn't look very good in terms of worst case performance. Let's see. What you been up to there, Jedi? Hmm. Not much, just playing some games and doing some chores. Yeah. Yeah, I was doing some chores yesterday. Hence the reason why I kind of got started on the Warframe gaming a little bit late. But let's see. Hmm. Seven. Hmm. Time complexity of this algorithm using Fibonacci heaps and the implementation of Dijkstra's algorithm is that the algorithm uses VE time for Bellman fourth stage of the algorithm and V log V plus E for each of the V instantiations of Dijkstra's algorithm. Thus, when the graph is sparse, total time can be faster than Floyd-Walsh algorithm. Hmm. So, but problem is that that's a still worse than Dijkstra's though. The fact that it uses Dijkstra's to continue working the on it. It's like, wait, what? You're multiplying V into both portions of Dijkstra's algorithm, worst case. So that's not exactly ideal. So I'm gonna kind of put this under the yeah, let's not do that. We'll go ahead and put that in the bad section there. Don't need that one. Jump point search. Okay, what's this all about? Computer science, jump point search is optimization of the A-star search algorithm for uniform cost grids. Okay, mine is a uniform cost that there's no like varying cost, so it reduces symmet symmetries and the search procedure by means of graph pruning. Interesting, okay. Eliminating certain nodes in the grid based on the assumptions that we made around the current node's neighbors, as long as certain conditions related to the grid are satisfied. As a result, the algorithm can consider long jumps along straight, horizontal, vertical, or diagonal lines in the grid, rather than small steps from one grid position to the next that ordinary A-star considers. Interesting. Okay. Jump point search preserves A-star optimality, but potentially reducing its running time by an order of magnitude. Detection provides algorithms for neighbor and pruning and identifying successors. Original algorithm for neighbor pruning allowed corner cutting to occur, which meant the algorithm could only be used for removing agents with zero width, limiting its application to either real-life agents, robotics, or simulations. And modified pruning rules for applications where corner cutting is not allowed. The following year, the paper also presents the algorithm for pre-processing the grid in order to minimize online search times. Reconvening jumps on the grid and stronger pruning rules. I'm kind of curious as to what this can do, especially seeing that, it's supposedly preserving the uh, A-stars, overall ability, but at the same time could potentially, um, you know, reduce the running time. So I'm kind of liking that right at the moment. We'll probably need a little bit more research on that, seeing that it's not really giving me any kind of, um, worst case scenario on this. So, okay, not showing worst case. Search needed. Okay. Let's see. Let's see. Serves A-stars. Optimality. Potentially reducing running time by an order of magnitude. Okay. So far we have two potentials that might be a little bit better than A-star. more research needed. But that's what today is all about anyway, so research into this. Okay, so let's go ahead and save this one. There we go. Okay, Kishkal's algorithm. Spinning for forest and undirected edge-weighted craft. It's not really edge-weighted, so that's something that is kind of going against it already. Um, okay. Hmm. First set of edges. Two versus part of the same tree. Let's see. Okay. Let's see. AD and CE are the shortest edges with length 5. AD has been arbitrarily chosen, so it is highlighted. C is now the shortest edge, does not form a cycle with length B and length 5, so it's highlighted with the second edge. So both are highlighted there. The edge DF with length 6 is highlighted using much the same method. Next shortest edges are AB and BE. Both length 7, AB is chosen arbitrarily and is highlighted. The edge BD has been highlighted in red because there already exists a path in green between B and D. So it would form a cycle if it were chosen. Yeah, um, so if you were like trying to get to B, you know, and if you were going like, D to B straight off the bat, then 9 would be the quickest path for it. Um, but at the same time, if this is kind of using the finding the edges on this, then you know then it's gonna find these first and then kind of cause a problem because while D and B has the shortest length of 9, um, the edges are trying to say, hey, you have to go this particular direction. So not exactly efficient. in those kind of in that kind of regard. And even then, this I don't have any kind of weight to any of my pathing from one hex tile to another. So this algorithm right now is not going to be working very well for me. Yeah, I think no, I'm not really seeing any good locations or good information showing the worst case performance. I'm not really seeing any. Hmm, see, total time is O. E log E is equal to E log V. Hmm. But, I mean, don't really need the edges on this. Oh. Hmm. I can probably just go ahead and bypass this. Um, no, given worst case performance needed edge weights work. Okay. I mean, if you did have edge weights, then this could be fairly useful. But yeah, not really for me. Okay. Lexicographic breadth first search. Lex BFS. Linear time algorithm for ordering the vertices of a graph. Algorithm is different from the breadth first search, but it produces an ordering that's consistent with breadth first search. Idea of partition refinement. First developed by Dr. Rose, E. Tarjan, and Georges Luker. Details survey of the topics and use subroutine and graph algorithms, including the recognition of quadral graphs and optimal coloring of distance arbitrary graphs. Hmm. Hmm. Still there, Jedi, or you went back to doing chores? Hmm. In a mission? Ah, okay. No worries. Um, I figure um, I'd let you know now that you'll probably want to if you're able to try to make this upcoming Saturday or try to um, try to join me on my Warframe uh, stream next Saturday because um, yesterday I was able to get the helmet, so I'll be doing all that next week. So sacrificing a lot of the my non prime warframes into it. So not all of them, just a few. Okay, let's see. Still need Still need to do the helmet stuff on my PC account. Yeah, it took me a while to get through the grind for it, but I was able to get enough rep together to get the accounts and um, already had the um, mining forging resource. So um, Mr. Stab was able to kind of help me out with the hunting specific tags. So that was a little bit of an ordeal, but he was able to kind of help me out with that. So, but we have that going to be having that ready to be installed next Saturday. So I'll be doing a lot of sacrificing and looking up um, what can be done with the helmet and on all that kind of jazz. So yeah, hunting for tags can be a pedo when you're looking for specific ones. Yeah, pretty much. Um, it also doesn't help when if you don't have like the echo lures because apparently one of the tags necessary um, for getting the rank up, you needed an echo lure to find the rarest of the animals. So that was kind of irritating. My dojo should be finished by next weekend for sure. It's coming along pretty nice. Nice. Let's see. I'm not quite sure whether or not this is going to be good or not. It's not really showing me a good worst case right at this point. And I'm not really seeing anything that is, um, anything that basically screams out at me that, hey, you really shouldn't be using this. So, at least not for my particular use anyway. Mm, I might need to just kind of come back to this one. So, more research needed. I'll just go ahead and put it up there for now. Okay, forward Warshall algorithm. Finding weighted graph, which I do not have. Positive and negative edge weights, but with no negative cycles. I'll find links, short paths between all pairs of vertices. It does not return details of the paths themselves. It's possible simple modifications to the algorithm. Hmm. Worst case and average performance is the same, huh? That's not exactly ideal. I mean, if you look at worst case scenario, log v log v is going to be a better solution than um, v to the power 3. So already we're looking at you know, adding Floyd Marshall to, my bad section, or, a section that's not very useful, obviously. But let's see. Maybe there might be something here that can be a little bit more helpful, but probably not. I mean, the fact that we're already seeing edge weights, which my graph does not have, or there's no edge weights in the, um, in traversal from one hex tile to another. So, already we're we're seeing like, two strikes against this particular other algorithm already. So, let's see. Yeah. Hmm. Let's see. For the Russell algorithm is a good choice for committing paths between all pairs of vertices in a dense graph, in which most or all pairs of vertices are connected by edges. For sparse graphs with non-negative edge weights, their choice is to use Dijkstra's algorithm from each possible starting vertex, since the runtime for repeated Dijkstra using Fibonacci heap is better than the V uh, V to the power of 3. So, yeah. So, let's go that. E to the power of 3. So, don't need that. There we go. Fringe search. It finds least cost path from given initial node to one goal node. Essence fringe search is a middle ground between A star and a deepening A star variant. Initial path cost of goal. Three major inefficiencies, IDA star, repeats states, multiple, sometimes non-optimal paths. So by keeping a cache of visited states, and they're memory enhanced, so uses some storage, search for iterates in a new threshold, search implements these improvements in the EA by making use of a data structure that is more or less two lists to iterate or frontier or fringe of the search tree. List now source the current iteration, other list later source the immediate next iteration. So from the root node of the search tree, now will be the root, and later will be the empty. Takes one of two actions. If head is greater than current threshold, remove head from now and append it to end of later. Save head from next iteration. Otherwise, if head is less than equal to threshold, and head and discard head, considering its children, adding them to the beginning of the now. Okay. Excuse me. Let's see. Passable obstacles. Hmm. When tested on grid-based environments typical of computer games, including impassable obstacles, Fringe outperformed A-Star by some 10% to 40%, depending on the use of tiles. Rock tiles. Possible further improvements include use of a data structure that lends itself more easily to caches. Interesting. And the nodes that precede the current node. Later proportion. And now list using array of pre-allocated nodes and list for each node and grid. Access time to nodes and list is reduced to a constant. Accumulated marked array allows lookup of a node and a list to be done at a constant time. G is stored in a hash table and our last marker array is stored. Lookup not a node has been visited before. Cache entry is valid. Hmm. Um, hmm. I mean, I appreciate the fact that Fringe is supposedly faster, outperforming A-Star by 10 to 40%. I do appreciate that. I may want to look into that a little bit more. So let's go ahead. Don't really have any, it's not really listing any kind of worst case scenario in this at all. So, um, go ahead and just kind of put this out as a more research needed. Um, 10 to 40% performance boost over A-Star. Okay, we'll go ahead and put this down here in the goods section for now. We'll go ahead and get the gonna move French search over here, and we'll move on with the rest of our um, we'll move on. Um, Search for tree root. Sometimes search key explores all the neighborhood nodes and present depth prior to moving on to the nodes in the next depth level. So, um, it's not really kind of showing it here, but no, it's not really showing it, but you can kind of get an idea as to what it's all about just from the numbering system here. So one, you look at one, you find out all the nodes that is connected to one, and you see two, three, and four. Um, so one says, okay, we're gonna kind of put that over to the side. We're gonna save that. Now say we're like looking for 11, for example. Okay. We look at two because that's like the next one on the um, next in the queue. Basically, you go to one, you look at all the connection and no connections. You see two, three, four. You throw those in that particular order, two, then three, then four, into a queue so that the next one that gets popped off is the two. Um, so then from two, we see that there's five and six connected to it. So we add 5 and 6 to the queue. So now we have 3, 4, 5, and 6 to this. But we haven't reached our destination yet. So we now look at 3. 3 doesn't have any nodes that, hasn't already been added to the queue and um, isn't really looking for anything else for us. So, or really isn't seeing anything else. So 3 does nothing. We look at 4 and we see we have 7 and 8 connected to it, but that's about it. So we go ahead and add 7 and 8 into the queue. So now we have 5, 6, 7, 8 in our queue. And then we kind of close down 4 in that particular case. Like, we say, hey, 1, 2, 4, is the path for 7, for example. Um, so now we move on to like the next number, which is 5. We see 9 and 10, so we add those to the queue. So now we have 6, 7, 8, 9, and 10. Not really sitting, not finding our destination, not really seeing anything else to our destination. So now we look at 6, not seeing any kind of connections with 6 with anything else. So we go ahead and close that one down. Then we see 7, and it has nodes 11 and 12. Now, 11 is our destination, and seeing that there isn't any other um, quicker route to this particular destination, and the fact that 11 is our end node, we can just basically say, hey, take 11, we're done. We don't need the queue anymore. We just found 1, 4, 7 to 11. So let's see. Let's see, breadth first search. Okay. But overall, it might not be something that we really need to kind of go for. But then again, A star is basically essentially a breadth first search itself. Um, so we'll just kind of throw this in the bed anyway. We don't really need it. So Okay, so we'll go ahead and close that one out. Okay. Okay, numeric analysis, numerical, mathematical optimization, what shorter route is likely to be attained, optimal solutions for convex problems. The problems will find only local optima solutions that can be improved upon by any neighboring configurations. Hmm. Relative simplicity of the algorithm makes it popular first choice among optimizing algorithms. It's used wisely in artificial intelligence for reaching a goal state from a starting node. Different choices for next nodes and starting nodes are used. Related algorithms, although more advanced algorithms such as simulated annealing research results in some works just as well and produce a better solution result than other algorithms when the amount of time available to perform search is limited, such as to real-time systems, so long as a small number of increments typically converges on a good solution, the optimal solution, or close approximation. At the other extreme, bubble sort can be viewed as a hill climbing algorithm. Every adjacent element exchange decreases the number of disordered element pairs, yet this approach is far from efficient for even modest n, as the number of exchanges required grows quadratically. Oof, okay. Let's see. Uh, hmm. Hill climbers only adjust one element of vector at a time. Each step will move in an axis line. Target function increase the narrow ridge. Hmm. I'm not really seeing any like good. Well, I mean there is Cedar code on this particular page. Hmm. But it looks like there's a lot of this is kind of checking out the edges, checking out the distance between one vector and another, you know, um, with a um, with the value kind of changing based off of you know, the edge between the two could potentially be um, the main problem with this particular algorithm because we don't really have any kind of weight on the edges. So, hmm, I think I might need some more research on this one. I'm not really seeing anything here. Hmm, I don't know. I don't know if this is something that I really need though, because I don't have any like hills or valleys or anything along those lines. I don't have any kind of weights on my edges and light, so everything's going to be fairly standard. Everything's going to be the same height and all that. So, hmm. Okay, folks, I'm gonna need to use the restroom here real quick, so I shall return in just a moment. So be right back. All right. Sorry about that, folks. All right. Sorry. I'm not sure why I'm sleepy. I thought I got enough sleep last night, but I guess not. Um, all right. Let's continue our research on this, shall we? Um, so I'm not 100% sure I really need to research hill climbing all that much. Um, because um, once again, this is getting into areas where you have, not only the vertices um, being of different value, but you also have the edges having different values. Problem is um, with my particular map, I have no weights on any of this. So, um, so I don't necessarily need to worry too much um, about hill climbing, weight, edge weights and the like. So first closer node is chosen. Yeah, which there's no difference in distance on these. So the problem with this one is the fact that we don't know. Um, I mean, we could figure out um, the distance between where the current player is at and the um, and where they need to go, and find out the distance there. So you could, pick the one um, textile that's closest to the destination. But in a node, that doesn't necessarily mean that that's the best solution. Hmm. does not determine all neighbors before deciding how to move. Rather, it selects a neighbor at random and decides whether to move to the neighbor or examine another. It's like, okay, that doesn't really help either. Um, you know, this doesn't really help in the fact that, you know, in a maze, you know, even trying to go in a straight line to your destination isn't going to always work for you, okay? Because there might be a different path. Okay, that's longer than trying to go straight at it. Okay, you're probably going to be hit with a roadblock or, you know, some kind of barrier that prevents you from getting, you know, to get into that destination based off of where you're at. So, yeah, I don't know. Everything's kind of screaming to me that, you know, hill climbing is not exactly an ideal um, pathing search algorithm for me in this particular case. Welcome back there, Jedi. So, don't have a good um, worst case performance on this, but um, so um, um, just just feeling like this one needs weights to form. That might not be true. That might not be true on this, but the fact that, you know, everything here is just kind of saying, hey, you know, what is the distance between, you know, the node that you're currently on and the node that you're trying to get to, and it's like there's no distance. So this is just kind of screaming at me that there's um, you know, weights is kind of in play on this particular um, pseudocode and the like. So, okay. Lifelong planning A star. Incremental heuristic search rather than based on A star. It was first described in Kone Chedev in 2001. Is an incremental version of A star, which can adapt to changes in the graph without recalculating the entire graph. Okay. By updating the G values distance from start from the previous search during the current search to correct them when necessary. Like A star, LPA uses a heuristic which is a lower boundary for the cost of the path from a given node to the goal. Heuristic is admissible if it's guaranteed to be non-negative, 0 being admissible, never greater than the cost of the cheapest path to the goal. With the exception of the start and goal node, each node n has predecessors and successors. Okay. Any node from which an edge leads towards n is a predecessor of n. Any node to which an edge leads from n is a successor to n. Following description, these two terms refer only to the immediate predecessors and successors, not to predecessors or not to predecessors of predecessors or successors of successors. Start distance estimates. LPA maintains two estimates of start distance for each node. Okay. G and the previous calculated G value, start distance as in A star, arch as a look ahead value based on the G values of the node's predecessors, minimum all predecessor. The cost of the edge connecting X and Y for the start node, the following always holds true. Nodes are equally consistent. The shortest path can be determined with A star. Edge costs change. Consistency needs to be reestablished only if those nodes which are relevant for the root. Hmm. Hmm. Okay. Okay. Okay, so based off of what I'm reading here, the lifeline planning A, which might be something that I might be interested in working on here. This is basically storing like the best path for a particular node to like another node on the overall map. Um, so and it feels like this all kind of takes place at the very beginning. All this um, information is kind of collected at the very beginning um, of the map generation. You can kind of work on each one of these particular nodes um, at the very beginning of the map creation, and you can just kind of build this large array of information for each node saying, hey, you want to get to this node? Okay, well, you want to go to this particular node next to me to get there. And obviously, if something changes, like hey, um, resource completely gets drained on one particular node that it completely opens up, then obviously things need to kind of reevaluate. But that might require a lot of kind of calculations based off of the map size. Hmm, I don't know. The map has the potential for changing fairly often, so um, having it to try to figure out, you know, um, whether or not a route has been modified, um, doesn't really fill me with a huge amount of confidence. Hmm, what am I gonna do? Hmm. I don't know. Each node is expanded at most twice for each run. Um, Locally over consistent nodes are expanded at most once per LPA run. Each run has similar performance to A star, which visits each node at most once. Keys of the node expand for each run are monotonically non-decreasing over time, as is the case with A star. Most informed and thus larger the heuristics are, while still satisfying the missability criteria, the fewer nodes need to be expanded. Q implementation has a significant impact on performance, as in A star. Using a Fibonacci heap can lead to a significant performance increase over less efficient implementations. Hmm. we don't really have a worst case scenario on this, but I'm kind of liking where it's kind of going on this. So we'll go ahead and put that in the good section here. So here's where so from what I can understand of this lifelong planning A star. So um let's go ahead and um let's go ahead and bring up like a different graph or something along those lines. Let me bring up a tree here, or at least try to. Um, okay, so let's just use this little illustration here. Okay, so from what I'm gathering from the um, this lifelong planning A star, okay, it is basically taking your A star searches that you're doing here, and for each node, it is basically saying, hey, this node, trying to get to this other node in on the map, um, you're gonna want to go, based off of your results on an A star search, it's basically saying you're gonna want to go to this particular node in order to follow the right kind of path. Um, now, now that might be really good if your map doesn't change whatsoever. Okay, um, because once it does like all the A stars once, then it has an idea as to like, hey, you're at this node and you're trying to get to that node. Well, you're going to need to go to that node. So, um, so it has a rough idea already as to where to go. So you don't have to keep on recalculating the pathing each and every single time because it already knows that initial path. It already has a path already kind of built out for you. Or at least that's what I'm getting from this lifelong planning. Okay, it has, um, you know, if you're at a, you're currently visiting at a particular node and you're trying to get to, you know, another node for your goal, you know, it's already done all the A stars for the map, stored all those, stored all the best solutions so that you can just kind of look through, hey, I'm trying to get to this node. What's the best place for me to go? And it's going to go, oh, well, you're going to need to go to this particular node to find the best path. So, and this can be used by anyone. Okay, so you don't have to redo A star over and over and over again, so um, so this seems like a really useful tool, for um, if your map doesn't change at all or anything along those lines, your AI can just kind of go the way it kind of needs to go based off of all the A stars that has kind of come before it. Um, The problem with this though is the fact that my map does change a little. Okay, it does allow for um, resources to be removed and barriers to be put up, which blocks which can block pathing, both for the enemies and for the humans. So um, that's one of the reasons why I'm kind of hesitant on the lifelong planning, because while lifelong planning is great, in that the um, you can potentially have all of our agents kind of walking around all at once, um, collecting resources and um, and it's their pathing could be different for each one. Um, you know, you wouldn't have to rerun the A star algorithm each and every single time they reach a destination node. The lifeline planning already has, the optimal solution, which it might need to reevaluate based off of, if a barrier goes up or resource gets depleted. So it might need to kind of recalculate. But I mean, once that recalculation is done, then once again, I'm not relying, I'm not forcing the AIs themselves um, to do an A star each and every single time. Hmm. So that's where I'm still kind of hesitant on it because um, the because there's potential for change in the overall map. So that's why I'm like, it's good, but is it something that I'm gonna want? Not sure. We'll go ahead and put it in our list over here for things to kind of keep on. Um, Something to kind of keep on looking into and the like. So, okay. Rufka's algorithm is a greedy algorithm for finding the minimum spanning tree in a graph. And yeah, I don't need to worry about this because we're not dealing with edge weights or anything along those lines. So I already one strike against it. Hmm. Yeah, I don't think there's anything here that I really want. The fact that it's talking about the edges and like is um, our graph G whose edges have distinct weights. I don't have that, so but don't have any kind of worst case scenario or anything along those lines really, so I'm not really seeing anything off the from what I can see, so but we don't necessarily need to worry about it too much because um, so we'll go ahead and copy that. So no given worst case performance uh, needs weights to perform. That's a given. So oh, don't need to save it. Okay. So we can go ahead and close that one down. Don't need it. Branch and bound. Okay. Hmm. 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 Okay, so from what I can see of this, um, branch and bound seems like it's a fairly similar design to Dijkstra's and A-Search and the like. So I'm not seeing any kind of worst case performance or anything along those lines. Um, but I think we're okay with just kind of putting this down in the my little bad section. Um, not being very efficient overall. So, Okay, so sorry about that. Okay, so we're gonna go ahead and just kind of put this down there. Um, 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 early version of A star and the like. So we don't really need this anymore. Okay, Chrome, come on. What are you doing on me? Okay, prims. Create an algorithm that finds a minimum spanning tree with a weighted undirected graph. Don't have weighted, so already we're at a single strike here. From the tree, including every vertex, where total weight of all the edges in a tree is minimized. Algorithm operates by building this tree one vertex at a time from the arbitrary starting vertex. Each step adding the cheapest possible connection from the tree to another vertex. Hmm. Yeah, already we're kind of at a point where this isn't really very helpful for our needs. So yeah, yeah, I'm gonna go ahead and move this one down to the bad, seeing that it uses edges or edge weights. So I'm not seeing a worst case performance. Hmm. I mean, I guess that would be the complexity or whatnot. So go ahead and put this down. Using edge weights. So not something that we want. Okay, simplified memory bounded A star. Shortest path algorithm based on the A star algorithm. Main advantage of the SMAs that uses a bounded memory, while the A star algorithm might need exponential memory. All their characteristics of SMA star are inherited from A star. Like A star expands most promising branches according to heuristic. What sets SMA star apart is that it prunes nodes whose expansion has revealed less promising than expected. The approach allows the algorithm to explore branches and backtrack to explore other branches. Expansion pruning nodes is driven by keeping two values of f for every node. Node x stores the value of fx, which estimates the cost of reaching a goal by taking the path through the node. The lower the value, the higher the priority. A star, this value is initialized to hx or gx. Is complete if the allowed memory is high enough to store the shallowest solution. The more of the allowed memory is high enough to store the solution, otherwise it will return to the solution that fits in the allowed memory. Allows repeated states as long as the memory bound allows it. Will use all memory available. Margin memory bound of the algorithm will only speed up the calculation when the memory is available to contain an entire search tree. The calculation has an optimal speed. Because those nodes are deleted, SMA also has to remember the f cost of the best friend child, the parent node. Hmm. I don't know if I really want to get rid of um, I don't know if I really want to get rid of, branches that lead to nowhere because, um, we're at a point where we have agents that could potentially go all over the map, and um, if they're going all over the map, then they're going to need to know, you know, um, where exactly they're going, how it gets there, and how to get a return from said point. So don't think this one is going to be that useful for me in this particular case. So I'm assuming the worst case is probably about the same as A star. Um, so similar to A star, but allows for pruning of nodes could potentially cause issues. All right, let's see. Bidirectional search is a graph search algorithm that finds the shortest path from the initial vertex to the goal vertex in a directed graph. It runs two simultaneous searches, one forward from the initial state and one back from the goal, stopping when the two meet. The reason for this approach is that in many cases it is faster. For instance, if a simplified model of search problem complexity, in which both searches expand the tree with branching factor b. The distance from start to goal is d. Each of these two searches has complexity O, B, D, B to the power of D divided by 2. And these two search times is much less than the big O. The attrition B to the power of D complexity would result from a single search from the beginning to the goal. As in A star search, bidirectional search can be guided by a heuristic estimate of the remaining distance to the goal. A forward tree and from the start and the backward tree. First one to design and implement a bidirectional heuristic search. Hmm. I think, well, this one doesn't really have any particular, um, um, well, this one doesn't necessarily have any particular helpful um, algorithms or worst case scenarios or anything along those lines. It's definitely something that you can use if you're kind of working like an A star. You can just kind of go, um, you can have, one node there and another node there and just kind of have it kind of flow to the point of, connecting with each other. So in other words, um, take the A star here. So, um, you know, while it's trying to start from this point here, for example, expanding um, towards its destination, so can the end point here kind of expand out, trying to get to this point as well. So eventually they'll get to a point where they're gonna kind of meet like right in the center. So they'll be able to kind of connect there and go, hey, this is the shortest line. So um, at least that's the kind of the point of it. Um, so while it's not something that is its own, unique algorithm, it is definitely something that we can try to use, if we're going to be doing like an A star. So, full for A star. Okay, let's see. Next, let's see. As for search, as a search algorithm that explores a graph by expanding the most promising node. A star search algorithm is an example of best first search algorithm, as is B star. Best first algorithm is often used for pathfinding and combinatorial search. Neither A star nor B star is a greedy best first search, as they incorporate the distance from the start in addition to estimated distances to the goal. So it's pretty much an A star, so um, we don't need to worry about this. So we can just kind of put that down there. Um, Basically, A star. Don't need to worry about that. Okay, now if I remember correctly, last week we were kind of working on this already, and we were kind of looking into these particular um, we were kind of looking into these particular algorithms last week. So I might actually be kind of repeating myself a little bit here. So apologies to anyone that was kind of that's been kind of following me along these lines on this particular portion of pathing. But um, I want to get this kind of ironed out now. So um, okay, so Bellman-Ford algorithm can be shortest paths from a single source for choice to all the other vertices in a weighted digraph. We're not weighted, so we don't. That's already kind of first strike on this. It is slower than Dijkstra's algorithm. Second strike. Hmm. Well, we already know Billman Ford's already kind of worse. So, um, so let's see. Okay. Um, Later graph. not needed. Now, some of you might be wondering, okay, Jim, what's all this, VE, you know, log V, so on and so forth, all about? Um, well, um, it has basically the um, gosh, um, let me try to explain, and hopefully it will kind of help you. Now, if I remember correctly, um, yeah, okay, so um, V is the number of vertices, and E is the number of edges. So, so when you're looking at a graph, let's go ahead and pull up one of those. Um, or at least let's try to bring up a graph of some kind so I can try to show what I'm talking about, which it's not really finding a good one right at the moment. Okay, let's just maybe open up this one here real quick. Nope, that was the wrong one. Da, 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 da. There we go. Okay, so take this kind of a graph for example. Okay, um, vertices is basically the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there'd be 12 vertices in this particular case. Okay. Edges is basically the connectors between these two. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So um, so these kind of calculations here, like for example, in this particular case of 12 vertices and 11 edges, okay, this Bell and Ford algorithm, you're basically looking at 12 times 11 as the worst case scenario of the number of searches that you have the potential of doing on that. So here let me bring up calculators so I can kind of show those kind of values for you here. So um, so the 12 times 11, that you're going to be getting 132 potential searches, um, as the worst case, on for like the Bellman Ford, for example. Now, if you use Dijkstra's, okay, Dijkstra's algorithm there, which we've already kind of shown the worst case here. So um, we have the 12 plus 11 times log 11. Okay, so um, let me switch over to scientific. So log 11, 11 log. Okay, so there's that log of 11 there. Multiply that by 11 there. So that's that's our current value for this portion right here. and then you add that to the 12, and that's the total number of searches that you have, you know, a worst case in Dijkstra's in this particular case. So that's why, you know, um, in comparison to Billman's Ford, which has, basically 12 times 11 as worst case, you're now looking at, potentially, 23, you know, versus what was it, 132? So, yeah, just a little bit better overall in terms of the performance. Okay, this is worst case, meaning that 23 is um, the maximum amount of searches to get to its destination, for example. Okay, whereas this one requires 132. So just kind of wanted to point that out for anyone that was kind of wondering about that. So obviously not the greatest. All right, we can go ahead and close that one out too. Don't need it there. Computer science beam search, first search algorithm that explores a graph by expanding the most promising node in a limited set. Well, how do you determine what's the most promising node? um, best for search that reduces memory requirements. Best for search is graph search that orders all partial solution states according to some heuristic. But beam search, only a predetermined number of best partial solutions are kept as candidates. Yeah, that's not exactly ideal in this particular case. Once again, seeing that I'm going to have agents potentially going around the map, um, I don't want I don't want them saying, "Hey, we're not never going to go to this particular portion of the map because it's not really efficient or anything along those lines." It's like, no, come on, this isn't what I want for this. So, um, we do want them to be able to, um, to be able to kind of go around the map, go to nodes that are on the map, and not you know have any particular moment in time where it was like, yeah, no, um, we're going to go ahead and say you're never going to be able to get there or get out of there at any particular moment in time. It's like, no, no, not exactly ideal. So, and the greater the beam width, the fewer states are pruned. Yeah, beam search is identical to breadth first search. Yeah, so doesn't really give you any kind of worst case scenario, but yeah. We're gonna go ahead and kind of put this in a little bad section here. Don't really need it. Um, see. Um, Prunes. Just gonna go ahead and ignore that for now. So, alright. Um, Classic textbook example of using backtracking in the 8 queens puzzle. As for all arrangements of 8 chess queens on a standard chessboard, so there are no queens attacks any other. Again, I don't think I really need anything here on this. There really isn't any kind of like major um, changes to there isn't really any kind of like major like algorithm portion to this, and it's feels a lot of kind of like brute force, um, which doesn't really help. Um, so yeah, we'll just go ahead and ignore that one. So um, see. Typically, brute force is not what you kind of want to do at all, if you can help it. You know, typically like brute force gives you like some of the um, worst case performances. You know, much like Bellman Ford here. You know, giving us 132, for example. So, um, the algorithm stores intervals for nodes of the tree as opposed to single point value estimates. And leaf nodes of the tree can be searched until one of the top level nodes has interval which is clearly best. Okay, so Okay. Not really seeing any kind of um, pseudocode or worst case scenario or anything along those lines for this. So we'll just go ahead and put this in the bad. Don't need it. Okay. Okay. Um, Once again, this is part, while this might work for, games such as chess or something along those lines, this isn't exactly ideal um, for my particular game um, um, because any kind of move might turn into something good afterwards. So the whole pruning is not exactly ideal. So we'll go ahead and remove that. Let's see, worst case performance. Let's see, pruning. Exactly ideal for what we're kind of looking for right at the moment. So, hmm. Hmm. Let's see. vertices, same but for search, we'll order them arbitrarily. Choose between V and W by output ordering of their second earliest predecessors. And one of them has a second earliest predecessor. It's already been output. That one is chosen if both same second earliest predecessor dies by considering the third earliest predecessor and so on. Breadth first search uses set partitioning data structure in order to produce the same ordering more efficiently, just as a standard breadth first search uses a queue data structure to produce its ordering efficiency. I don't really know if this is really anything useful for me or not. Initialize a sequence of sets to contain a single set containing all vertices. Initialize the output sequence of vertices to be empty. While set is non-empty, find and remove vertex V from the first set. The first set is now empty, remove it from here. Add V to the end of the output sequence. Still belongs to set S. Yeah, I don't think this is something that I'm gonna be kind of in need of. I think this has something that is basically gonna be kind of counter to what I'm looking for with the A star and the like. So Okay, so we'll just go ahead and move it down to the bad. Let's see. Sets goes against A star. And there's no given worst case performance. So, okay. So, um, so we'll go ahead and close that one out. I don't really need that right at the moment. We can go ahead and close this one out. Don't need that. This one's still this is still kind of going. I'm a little concerned here with the sheer amount of monsters and the like being produced and causing some slowdowns in animation, something that I'll need to kind of address a little bit later, but for now we'll go ahead and turn that off. Don't really need it going anymore right at the moment. Okay. So, let's see. Service path between a graph, which may represent, for example, networks. Um, okay. Hmm. Hmm. probably not going to be needing dextras either. So we can probably get rid of that as well. So, the reason why I'm saying we could probably get rid of it is, take this example here and kind of compare it to the same kind of problem with A star. So you can kind of clearly see the difference between the two here. So we'll go ahead and get rid of dextras as well. Um, First, then A star. Okay. Okay, so we got, a couple of algorithms that we can kind of work on a little bit. Now, bidirectional is pretty much, you know, good depending on what gets used. So, um, now we're gonna need to kind of research more of the D star, the jump point, the fringe search, and the LPA here to see whether or not it is indeed, and they are indeed better than A star in some fashion or another. And then we're gonna need to try to figure out look up examples of these to try to help us kind of get past or at least figure out the pseudocode for it all, so that we can tie it into our game here, so that we can try to figure out, um, you know, uh, which which one of the values we want to kind of go with. So let's go ahead and go ahead and copy all this. Um, so which of the following is the best? So okay. Okay, and there we go. So now we can just kind of get rid of these because we've already determined that don't really need them, don't really want them. So let's see. Okay. Let's see. Let's see. Version of Vistar that combines ideas from literature, piece finds shortest path from start giving class of graph change or vertices or deleted. Search is same as that of the version of Vistar that price ties. Price ties in favors of vertices, values. Hmm. Hmm. Lifeline planning A star. Let's see. Hmm. Can I actually download the PDF without any difficulty? I can. Looks like there's no like pages missing either on this, so hmm. Okay, so it's looking like I'm probably gonna be needing to um, looking on this a little bit more. So, I'm getting kind of tired here, though, folks. So, I think I'm gonna go ahead and kind of close it up early. I know 20 minutes early isn't too, is such a detriment. I know, um, but um, we've narrowed down what we're gonna be kind of needing to look at a little bit more. I mean, obviously, I can always use A star, but um, these other four here need to be kind of looked at a little bit more because, I do want to have a little bit more efficiency. Um, Seeing that I'm already looking at, um, I mean, when you're talking about like multiple different AI agents all on the same screen trying to figure out, where to go, finding the path and trying to build the A star repeatedly over and over and over again, then um, I'm not liking that kind of a scenario. I'd like to try to limit the amount of times that A star gets run. So, um, because when you're having multiple agents all at the same time trying to find the optimal path to a particular destination, then um, I don't want them. I don't want the game kind of cracking under the all the pressure of it all. So, but that's where we're gonna go ahead and call it for tonight. We'll go ahead and look into D star, jump point, fringe search, and LPA next week. So, um, if you have any experience with any of these, or if you want to discuss any of these a little bit more, or discuss, the ones that are kind of put into the bad section or something like that, or if you want to kind of discuss anything concerning this, um, my research into pathfinding, you can do so on my Discord. You can go there and we can have a discussion there if you'd like, concerning all of this. Um, or if you have any kind of questions concerning anything that was kind of brought up a little bit more on it, um, Discord's the place to go. You can try to use Twitter, but not a whole lot of um, character length on that to really have a good discussion. Um, or you can always go to my YouTube channel and put a comment in on that particular video when I um, put that up on my YouTube channel. Just comment right then and there. Um, I'll see it and I'll respond to whatever you might have to say. Um, if it's something that is worth replying to. Um, if it's like a rhetorical question or information or something like that that I might have already found out, then you know probably won't be needing a reply. Who knows? Okay, but that's where we're gonna go ahead and call it for tonight, there, folks. So, like I said, we'll look into all these next week. We'll go ahead and narrow down what we need for this game, and we'll move on from there. So, so that's where we're gonna go ahead and call it for now. So thank you very much for watching. I appreciate it. Hopefully I'll catch you next time. But until then, have a good night. Stay healthy, stay safe. I'll catch you strangers next time. Oh wait, I kind of cut things down a little bit, didn't I? Um, Sorry, brain's kind of. Um, yeah.
videos on my YouTube channel, links down below. Links to my Discord, my Patreon, and my Twitter account down below on my Twitch About page, as well as in the description of my YouTube videos. I have a schedule of everything that I do down on my Twitch About page, so if you're curious as to what I do during the week, as well as these weekend streams, that's right there. Shows what I do during the week, what days that I stream. It also shows what times I stream as well. So you can find that all there on the Twitch About page. So, okay, there we go. Now I'm out of here. So take care, folks. Have a good night.